Okay, so let's look at a couple of examples that involve these sorts of manipulations with complex numbers, in particular Euler's identity. So here we have an indefinite integral e to the x cosine 2x, and this is one of the ones that is in the notes. Okay, but I'm going to sort of fully work it out so you can kind of see it a little bit more clearly. All right, so if I look at this, one of the first things that I recognize is when I see something that has a cosine in it, I recognize right away that cosine typically means I'm looking at a real part of some sort of an exponential, right? So anytime I see a cosine, I go and I say, well, there's got to be a real part of something. And so in this case, I'm going to say it looks like it's the real part of e to the j 2x. All right, now the reason I say that is because I know that e to the j 2x is simply cosine 2x plus j sine 2x, like so. Okay? All right, well, so that tells me that if I take that integrand right there, that integrand should be able to be represented as the real part of e to the x cosine 2x plus j sine 2x. Okay. So I can say that e to the x cosine 2x is the real part of that complex number. And so the way that if I just to expand that, or I guess maybe to collapse that, I write that as the real part of e to the x times e to the j 2x, or as the real part of e to the x times 1 plus 2j, like so. Okay? So I can write this integral, instead of saying it's the integral of e to the x cosine 2x, I can say it's the integral of the real part of e to the x times 1 plus 2j dx. Okay? All right, now, at this point, I can basically say, you know what, this whole real part argument here, I can just say, well, why don't I just do the integral of e to the x 1 plus 2j dx. Just do that integral, and at the end, take the real part of the result. So in other words, I just want to peel off this integral and do it separately, and then come back and take the real part at the end. Okay? So that's what I'm going to do. All right, so here's how we'll approach that. So integral of e to the x times 1 plus 2j dx. I can use what's called, sort of it's just a substitution here. This guy looks like, to me, I can write it as e to the u du, right? Where I have u equal to x times 1 plus 2j, like so, right? So the way that I end up solving this guy, right, is I write 1 over 1 plus 2j times e to the 1 plus 2j x. And then at the end, there'd be a plus a constant, right? I can write the plus constant right now, but I'm not going to. I'm going to come back and do that part later, okay? All right, so let's keep going with this. So what I have to do is I ultimately am looking for the real part of this expression, right? So I basically have to get this guy expanded out so I can determine the real part of that expression. In other words, I need to get this guy into some format of a plus jb, where this a is the real part, okay? So to do that, I have to expand this whole thing out. So I write it like this. I have 1 over 1 plus 2j. I'm going to say I have e to the x, and then I'm going to expand that exponential into cosine of 2x plus j sine 2x. Okay? Like so. Next thing I got to do is, again, my goal is to get this whole thing into this form of a plus jb. Right now I have a real term and an imaginary term, but I also have a real and imaginary on the bottom. I need to not have a real and imaginary in the bottom. I need to have just a complete real term. So to do that, I multiply by the conjugate. So the top and bottom get multiplied by the conjugate, because when I multiply top and bottom by the conjugate, I'm technically multiplying by 1, right? And I keep the rest of this here. Okay. Now, to simplify this guy, I look at 1 plus 2j times 1 minus 2j. If I multiply complex conjugates like that, what I always get on the bottom is the real part squared plus the imaginary part squared. So I'm going to end up with that. Okay, oh sorry, not 1 plus 4 squared, but 1 plus 2 squared. So 1 plus 4. So I have 1 minus 2j times e to the x times cosine 2x plus j sine 2x. So now what I see is I have to multiply, I have to do essentially a multiplication of 1 minus 2j times this whole cosine 2x, j sine 2x piece. So this guy becomes essentially e to the x over 5 times, I'll do these terms one by one. So I have 1 times cosine 2x plus 1 times j sine 2x. So this guy becomes cosine 2x plus j sine 2x. And then I multiply the minus 2j by the cosine 2x. So I get minus 2j cosine 2x. And then I take 1 minus 2j and multiply it by j sine 2x. So that becomes plus 2 sine 2x. At that point, I have completely expanded this into a form a plus jb. So just to see that, let's do this real slow. Ax over e to the x over 5 times cosine 2x plus 2 sine 2x. Okay. And then I'm going to write this as plus j times e to the x over 5 sine 2x minus 2 cosine 2x. Okay? Now if I look carefully at this, what I have now is a, and I have plus j b, right? So now I've determined a real part and an imaginary part. Now back all the way to the beginning, what I said was my answer was the real part of this integral, right? So I computed just the integral. Now I need to take the real part of the result. So the real part of the result is just this guy here. So our answer here, the answer to this integral e to the x cosine 2x dx simply becomes the real part of that result. So e to the x over 5 times cosine 2x plus 2 sine 2x, like so. All right, and that exactly matches what we have in the notes. So helpful to maybe see how that guy kind of moves through slowly. We'll do another example in a separate video where we look at how to do that if we have something where we have an imaginary component.